Francisco. We are here live at Double K News. I'm Kinsey Keeble, and this is my co-host, Juliana Lopez.
Okay, Kinsey, I have a story to tell you. For lunch today, I had some enchiladas and beans, and they did not sit well with my stomach, and it gave me such bad gas.
Ew!
Woo!
Thanks for telling me. So, speaking of gas, we just got word of a new gas law that got discovered. The ideal gas law was discovered by Emily Clapperone. She got this theory from combining Boyle's law, Charles' law, Avogadro's law, combined law, and Gay-Lussac's law.
The ideal gas law is the mathematical relationship that has the standard temperature 0 degrees Celsius or 273 kelvins and pressure of 1 atmosphere, plus the molar volume STP, which is 22.4 liters per 1 mole. That is already combined into a single constant R. The equation for the ideal gas law is PV equals nRT.
P stands for the pressure. The units of pressure are measured in atmospheres, pounds per square inch, millimeters of mercury, torr, and kilopascals. Volume is represented by the letter V. Volume is measured by centimeters cubed, cubic centimeters, milliliters, liters, and STP. The molar volume of STP is 22.4 liters per 1 mole.
T stands for temperature. 0 degrees Celsius equals 273 kelvins. Absolute zero, which is 0 kelvins, means no particle movement. There is no negative kelvins. N stands for the number of moles. To figure out the volume of a substance from the mass of a substance, you use mass to volume stoichiometry. Now, in gas stoichiometry, for mass to volume, your equation can be how much volume of O2 is present in 3.45 grams of O2. Now, your balanced equation is 2H2 plus O2 yields to 2H2O. Now, how you would work that out is you put 3.45 grams of O2 over 1 times 1 mole of O2 over 31.998 grams of O2 over the constant of 22.4 liters over 1 mole of O2. And you multiply all of the top and multiply all of the bottom, and then you divide, which then gives you 3.45 times 1 times 22.4 over 1 times 31.998 times 1 is equal to 77.28 over 31.998, which is then gives you a final total of 2.42 liters of O2.
Now here's Sydney reporting from our neighboring studio, who will be telling us about each scientist's contributions to the ideal gas law and how each scientist discovered their own gas law.
Many chemists had dreamed of having an equation that describes relation of a gas molecule to its environment, such as pressure or temperature. However, they had encountered many different difficulties because of the fact that there always are other affecting factors such as an intermolecular forces. Despite this fact, chemists came up with a simple gas equation to study gas behavior while putting a blind eye to minor factors. When dealing with gas, a famous equation was used to relate all of the factors needed in order to solve a gas problem. This equation is known as the ideal gas equation. In some circles, the law is separately called Boyle's law, the pressure and volume relationship, Gay-Lussac's law, the pressure and temperature relationship, and Charles' law, the temperature-volume relationship. Often, these three relationships are combined into a single equation which incorporates all three at once. The term ideal gas law has nothing to do with this law being just the perfect law for gases. Rather, we take an ideal gas to be a gas that is sufficiently low density, such that the molecules of the gas in question are so far apart that they do not interact except with effectively elastic collisions. The equation is PV equals lowercase n RT. And back to Kinsey and Juliana.
The ideal gas law was developed in reference to ideal gases. The properties of ideal gases are summarized as the parts of the kinetic molecular theory. Oh goodness, here it comes again.
Oh man. Oh, you're supposed to.
Since the ideal gas law was derived from multiple other gas laws, we will show a few clips from the scientists themselves when they discovered their own gas laws. Here's the first clip from Robert Boyle. Goodness, I had to get that one out.
My law states that at a constant temperature for a fixed mass, the absolute pressure of the volume of the gas are inversely proportional. The law can also be in a slightly different manner for a product, and absolute pressure of volume is always constant.
So now we'll be talking about Boyle's law equation. Boyle's law is P1 V1 equals P2 V2. This stands for the initial pressure times the initial volume equals the final pressure times the final volume. If in a word problem, they might give you P1, V1, and P2. And so they want you to find your V2. So you have to isolate your V2. So what you would do is you would divide by P2 and divide both sides by P2. And so your equation for V2 would be P1 V1 over P2. And that would be your equation to find your final volume.
On the same topic, in 1802, Jacques Charles discovered his gas law. Here is a short clip of his remarkable discovery.
My law states that if a given quantity of gas is held at a constant pressure, its volume is directly proportional to the absolute temperature. As the temperature of the gas increases, the gas molecule will begin to move around more quickly and hit the walls of the container with more force. Thus, the volume will increase.
So the Charles law equation is V1 over T1 equals V2 over T2. The variables stand for initial volume divided by the initial temperature, which equals the final volume divided by the final temperature. A more friendly way to use this equation is if you cross multiply these, and you get a new equation of V1 T2 equals V2 T1. Let's just say you were given a word problem that gave you V1, and they wanted you to find T2, and they also gave you V2 and T1. You would have to go through and isolate your V1, or your T2 actually, T2. So you would divide by your V1 on both sides. So your equation to find T2 will be V2 times T1 over V1. Charles' law has always been one of my favorite. In 1811, I remember us reporting Avogadro's law, which I have an awesome clip of. Woo!
For my research, I found that equal volumes of all gases at the same temperature and pressure have the same number of molecules. For a given mass of an ideal gas, the volume and amount of the gas are directly proportional if the temperature and pressure are constant.
Now I'm explaining Avogadro's law's equation. It is V1 over N1 equals V2 over N2. A more friendly way to work with this problem is if you cross multiply both of them. And you get a new equation that's V1 times N2 equals V2 times N1. If you, let's just say you get a word problem and they give you 3 out of the 4 equation or variables, you can have V1 VO2 equals V2, and then want you to find your N1. You would have to isolate your N1, so you would have to multiply V2 on both sides. So your new equation for N1 would be N1 equals V1 times N2 over V2. This equation right here, it says the volume initial divided by the number of moles initial equals the volume final divided by the number of moles final. In 1802, news came in about Joseph Louis Gay-Lussac's gas law. Here's a clip of Gay-Lussac's interview after his discovery.
Oh, goodness.
My law is an ideal gas law where at constant volume the pressure of an ideal gas is directly proportional to its absolute temperature. In other words, the pressure of a fixed amount of gas at a fixed volume is directly proportional to its temperature in kelvins.
Good. And now I will be explaining Gay-Lussac's law. The equation is your initial pressure over your initial temperature is equal to your final pressure over your final temperature. Now, a friendlier way to use this equation is to cross multiply your P1 and your T2 by your P2 and T1. Now, your new equation will be P1 T2 is equal to P2 times T1. Now, say you have an equation where they give you your initial pressure and your final temperature, and you're trying to find your initial pressure, and they give you your initial temperature. Now your new equation will be P1 T2 over T1 is equal to P2. Since you have to isolate your P2, you divide by T1 on both sides to cross out your T1 and leave your P2 alone. And so now your new equation will be P1 T2 over T1 is equal to P2.
In 1766, John Dalton also discovered a new gas law.
I promise that was my last one, I promise.
My law is the total pressure in a container is equivalent to the sum of all partial pressure of the component gas.
And now I will be explaining Dalton's law. The formula for Dalton's law is PT is equal to P1 plus P2 plus P3 plus so on and so on. And all you have to do to find your total pressure is add up all of your partial pressures, which will then give you your PT, which is your final pressure.
When we come back from commercial break, we will hear our weather forecast for the day from Hallie.
Going paintballing with your friends this weekend and don't have a CO2 canister? Well, stop by to Extreme Sports Company More. We are located on 5th Street in San Francisco. We have a large selection to choose from. Come and pick yours up today. Warning, even though paintballing is fun, make sure you keep your CO2 canister in a cool, dry, room temperature area so that it won't combust and explode. Here's an explanation about CO2 from famous scientist Jacqueline Barton.
Hello, I am Jacqueline, and I'm going to explain to you why you need to keep your CO2 canister in a room temperature area. Gases like CO2 are ideal gases, and its properties are summarized by the postulates of the kinetic molecular theory. The postulates are, the gas consists of individual particles in constant and random motion. The volume of the individual gas particles is small when compared to the distances between the gas particles. Collisions between gas particles are perfectly elastic. No energy is lost or gained. The individual particles do not attract or repel one another in any way. The pressure of the gas is due entirely to the force of the collisions of the gas particles with the walls of the container.
And now over to Hallie for today's forecast.
Thank you, ladies. Today is scorching hot with a high of 97 and a low of 92. Everyone, make sure you're wearing plenty of sunscreen if you're going outside today for protection against the harmful ultraviolet rays from the sun. Did anyone see that pretty rainbow? Speaking of rainbows, here's your fact of the day. Rainbows are the only electromagnetic wave we can see. Each color has a different wavelength. Red has the longest wavelength and violet has the shortest wavelength. When all the waves are seen together, they make a white light. And here is a demonstration and a picture of an electromagnetic spectrum. Back to you, ladies.
Thank you, Hallie. We've enjoyed bringing you your daily news.
Make sure to come back tomorrow for another news segment on gas.
Bye!